Good morning, everyone. Thank you for being here. My name is Naksatra Premanand and I'm from the Computational Science program. Today, I'll be presenting my project titled Tunnel Flood Detection System with Barrier Control and Notification Mechanism. This project addresses the critical issue of flooding in Malaysian tunnels, which poses significant risks to public safety and infrastructure, especially during monsoon season. The lack of dedicated flood detection system in tunnels has led to delays in response, accidents, and costly damages. In this presentation, I will discuss the problem statement, the objectives of the project, and the literature review that inform the design. I will then walk you through the methodology, the tools and technology used, and the proposed system. I will also explain the data flow diagram, followed by the conclusion and future works to improve and expand the system. Moving to the next slide, let's discuss the impact of flooding in Malaysia. Flooding remains a significant challenge, particularly during the monsoon season when heavy rainfall and climate instability increase the risk. For instance, during the 2021 to 2022 monsoon season, floods caused an estimated Rm 6.1 billion in damages across the country. The consequences of these floods include road closures, which disrupt transportation networks, infrastructure failures, leading to costly repairs and even fatalities, highlighting the critical need for improved flood management solutions. Tunnels, in particular, are especially vulnerable as they are often lack proper flood detection systems, resulting in delayed responses and significant safety hazards. This underscores the necessity for a reliable, real-time flood detection system to protect infrastructure and save lives. Moving further into the problem statement, tunnels are particularly at risk during floods due to lack of dedicated flood warning systems. Without proper monitoring systems in place, responses to rising water levels are often delayed, leaving tunnels vulnerable to dangerous situations. Additionally, the absence of automated system makes these environments even more prone to sudden flooding, especially during rainfall. This lack of proactive measures results in severe consequences such as accidents, structural damage, and costly emergency responses, all of which could have been prevented with an effective flood management solution. This project aims to tackle these challenges by introducing a real-time flood detection and barrier control system specifically designed for tunnel environments. The solution will not only monitor water levels but also restrict access to tunnel during flooding and provide timely notifications to authorities. Moving on to the objectives of this project. The objectives of this project have been carefully designed to address the critical challenges of tunnel flooding and to ensure a comprehensive, automated, and efficient solution. Let me explain each objective in detail. The first and foremost objective is to implement a reliable system for detecting water levels in real time. To achieve this, ultrasonic sensors are deployed in the tunnel environment. These sensors operate by emitting sound waves and measuring the time it takes for the echoes to return after hitting the water surface. These precise measurements allows the system to calculate water levels with high accuracy, regardless of environmental factors such as lighting or air quality. The data collected from these sensors is transmitted to a central monitoring system where it can be processed and visualized in real time. This objective forms the backbone of the project, as early detection of rising water levels is essential for timely response and the prevention of accidents. The second objective focuses on the safety of both motorists and pedestrians through the integration of an automated barrier system. When the water level exceeds a predefined safety threshold determined during the calibration phase, the system automatically activates barriers at the tunnel entrances. This ensures that vehicles and pedestrians are prevented from entering a flooded tunnel, minimizing the risk of accidents, vehicle damage, and potential loss of life. The barriers are controlled by servo motors, which provide precise and reliable operation. By automating this process, the system eliminates the delays and potential human error associated with manual intervention, allowing for a rapid and effective response to dangerous situations. This objective directly addresses the critical safety gaps in traditional flood management systems. The third objective focuses on enhancing communication during flood events by implementing real-time notification system. Once a flood condition is detected, the system immediately sends alert to the relevant authorities. These alerts are sent via a web-based platform that provides detailed information, including the current water level, the activation status of the barriers, and any changes in the situation. This ensures that the authorities are equipped with actionable data, enabling them to coordinate emergency responses more effectively. Users can monitor the system in real time, visualize data trends, and even remotely access historical data to improve future decision making. The fourth objective is the development of a scaled-down physical model of the tunnel flood detection system. This model serves multiple processes. First, it provides a tangible demonstration of the system's functionality, allowing stakeholders to understand how it works in real-world scenarios. Second, it serves as a valuable testing platform for refining the system's components and ensuring their reliability under simulated flood conditions. The physical model incorporates all key components, including ultrasonic sensors, barriers, and traffic lights, as well as water reservoir to simulate rising water levels. By replicating real-life conditions in a controlled environment, the objective helps to validate the system's performance and identify areas for improvement before full-scale deployment. The final objective is the integration of a traffic light control system to provide clear and intuitive guidance to drivers during flood events. This system works in tandem with the automated barriers, offering a visual indication of the tunnel's accessibility. For instance, when water levels are within safe limits, the traffic light remains green, signaling the tunnel is open. However, if water levels rise above the safety threshold, the light changes to red, indicating that the tunnel is closed. This visual communication is critical for managing traffic effectively and ensuring public safety, especially in emergencies where quick decisions are required. The traffic light system reduces confusions, enhances awareness, and works as an additional layer of protection alongside the automated barriers. As part of the literature review, we analyzed several existing flood detection and management systems to understand their features, strengths, and limitations. Let me highlight three notable systems that inform the development of our proposed solution. The first system is a flood monitoring and alerting system that leverages LoRaWAN technology. This system uses sensors to monitor water levels and rainfall intensity, transmitting data via long-range, low-power communication protocol called LoRaWAN. The data is sent to a cloud platform where it is processed and analyzed to generate alerts for authorities and residents. Key advantages of this system includes its scalability and real-time data transmission. making it suitable for both urban and rural flood-prone areas. However, this system does not incorporate automated responses such as barrier control or traffic management, which are critical for ensuring safety in tunnel environments. The second system is an automated flood water level sensor and alarm system which uses Arduino Uno microcontrollers and ultrasonic sensors to monitor rising water levels. When a dangerous level is detected, the system activates alarms such as buzzers and LED indicators to alert nearby residents. This system is cost effective and easy to deploy, making it ideal for smaller scale applications. However, it is limited to providing localized notifications and lacks features like remote monitoring, web based alerts, or automated barrier activation. The third system uses IoT technology integrated with Arduino microcontrollers and ultrasonic sensors to detect and monitor water levels in flood-prone areas. This data is sent to a cloud-based platform, enabling users to access real-time information via mobile app or web interface. This system emphasizes early detection and provides remote access to critical flood data. However, it does not include mechanisms to manage traffic or restrict access to flood areas, which are essential for ensuring safety in tunnels. While these systems are effective in monitoring and alerting about floods, they share significant limitations such as absence of automated barrier control, traffic management, and tunnel-specific adaptations. These gaps highlight the need for a more comprehensive solution which is addressed by the proposed tunnel flood detection system. Moving on to the methodology of our project. Our project followed the System Development Life Cycle SDLC methodology to ensure a structured approach. In the planning phase, we defined the project goal, developing a tunnel flood detection system with features like automatic barrier control, notifications, and traffic light management, and created a timeline using a Gantt chart. During the analysis phase, we reviewed existing systems to identify gaps such as the lack of automated responses and determine specific requirements like precise sensors and web-based interface. In the design phase, we developed system architecture, flowcharts, context diagram, ERD, and database structures to guide the development. The development phase involved assembling hardware components like ultrasonic sensors and programming like Arduino microcontroller in C or C++. We also created a web interface using HTML, CSS, JavaScript, and PHP to provide real-time monitoring. Testing was critical with unit integration and system testing performed like physical tunnel model to ensure functionality under simulated flood conditions. Finally, in the deployment and maintenance phase, we created a working prototype and outlined plans for outgoing maintenance, including sensor calibration, software updates to ensure long-term reliability. The tools and technologies to be used in our system are Arduino IDE for programming the Arduino, C or C++, HTML, CSS, and JavaScript for creating the web interface, XAMPP, a local server for back-end development and database management, and finally, Visual Code. Now, let me walk you through the benefits of our proposed system. The proposed tunnel flood detection system significantly enhances public safety by integrating advanced features such as automatic barriers that restrict access to flood areas, traffic management system that signal drivers to avoid unsafe roads, and real time alerts that provide timely warnings to authorities and residents. These measures work together to minimize risk, prevent accident, and ensure a safer environment during events. The proposed system ensures real time monitoring by utilizing advanced sensors to continuously track water levels and other environmental parameters. These constant data flows allows for immediate detections of potential flood risk, giving authorities and residents ample time to respond. The integration of IoT technology further enhances the system's ability to collect, analyze, and visualize data through user friendly platforms, making real time flood monitoring more accessible and efficient. Moving on to the next benefit, which is automated flood management. The system incorporates automated flood management mechanisms. When water level exceeds safe thresholds, barriers automatically restrict access to flooded tunnels, preventing vehicles and pedestrians from entering hazardous areas. Additionally, integrated traffic light system help to guide drivers to safer routes, ensuring public safety and reducing traffic congestion caused by flooding. To ensure consistent performance, the system is equipped with reliable power and communication modules, enabling uninterrupted operation even during emergencies. These components guarantee a continuous supply of real time data and alerts to authorities and residents. The system's robust design, which includes cloud based data storage and secure communication networks, ensures that critical information is delivered accurately and promptly, enhancing disaster preparedness and response. This data flow diagram represents the process flow for a tunnel flood detection system, detailing the steps taken when a flood event is detected. Here's a brief explanation. The process begins and it initiates the system. The system activates and initializes the water level sensors to monitor environmental conditions in real time. The sensors continuously measure water levels. If the water level exceeds a predefined safety threshold, the system proceeds to the next steps. If not, the process ends and the system continues monitoring. When water levels surpass the threshold, the system triggers automated barriers to prevent vehicles or pedestrians from entering the flooded area. Alongside barrier activation, traffic lights are adjusted to redirect traffic and warn drivers about unsafe conditions. The system also sends automated email alerts to notify relevant authorities or stakeholders about the flood situation. The process ends once the required actions are completed, ensuring the system is ready for continuous monitoring. Moving on to the conclusion. The proposed tunnel flood detection system provides an effective solution to mitigate flood risks in tunnels by integrating advanced monitoring and management technologies. It significantly enhances public safety through real time water level monitoring and automated barrier activation, preventing accidents and ensuring efficient traffic control during flood events. Timely notifications are sent to authorities, enabling quick and informed responses to mitigate potential damages. Additionally, the system is designed to be cost effective and scalable, making it suitable for deployment in various flood prone areas, ensuring broader protections and resilience against flood challenges. As we look toward the future, there are several key areas for improvement and expansion in our flood detection system. First is improved sensor technology. We envision that the next generation of our system incorporating more advanced sensor technologies. These upgrades will not only enhance the accuracy and durability of our sensors but also enable the monitoring of a wider range of environmental parameters. This will significantly improve the system's ability to reliably detect floods in various conditions. Next, power backup solutions is to ensure the system operates without interruption during power outages or emergencies. We propose the implementation of robust power backup solutions. Next would be flood prediction algorithm. Looking ahead, we can integrate predictive algorithms into the system, utilizing machine learning or AI to forecast potential flooding events. By analyzing historical data and weather patterns, this algorithm will enable us to anticipate flood and take proactive measures, enhancing preparedness and response efforts. Last but not least, integration with traffic management systems. Finally, we plan to integrate our flood detection system with broader traffic management systems. This will allow us to better optimize traffic flow during flood events, efficiently rerouting vehicles, and improving public safety across affected areas. That is all from me. Thank you.